Hey, I hope everybody's doing well. In this video, I want to make a connection between limits and continuity. And this is going to be the graphical version of things. So in a previous video, I had these pictures that described different forms of continuity. So in this particular video, I want to talk about how this relates to limit. So in this first removable discontinuity, I'm going to add a little bit here, and I'm going to add a little horizontal to the x-axis. And I'm going to label this with an x equals 4. And I'm also going to put a y-axis here, and this little dot here, I'm going to say has a y value of 5. So if this open circle actually existed in there, it would have coordinates 4, 5. So how do limits get involved in here? Well, notationally, if I write down x goes to 4 with a little plus sign here, that means from the right-hand side. That means on this side, as I walk to the left of the function, well, this is going to be equal to 5 because the little hole is at a height of 5. What's nice about this in this particular picture that it doesn't make a difference on which direction you go from the left or the right. We both get 5. But notice that in my jump discontinuity, my left continuous one, and my removable discontinuity, these are very, very different. So what I'm going to do here is I want to again put a x value of 4, but now I need two y values. And as soon as I say two y values, the left and the right-hand sides are going to have different answers for the limits. So I'll put a vertical axis over here. I'll say this particular open circle has a height of 5, and this has a height of 7. In other words, I have a jump of 2. So if I look at this particular problem, x approaches 4 from the right of my function. I'm on the right-hand side. I'm going to get an answer of 5. Now, do not be concerned where the filled-in dot is. If I am over here, I am closer to the number 5 than I am 7. And if I take the limit as x approaches 4 from the left of this function, I'm going to get 7. And what I want you to notice here is that, well, 5 is not equal to 7. I mean, we knew that a long, long time ago. But that's actually really, really important for us right now. In this particular problem, for the discontinuity here, I'm going to get a very similar thing as I do on the left continuous thing. But let me add something over here. For the removable discontinuity, f of 4 does not exist. There is no filled-in dot anywhere in this picture. But in the left continuous case, f of 4, well, where's the filled-in dot? Is it at a height of 5 or a height of 7, or it doesn't exist? But in this case, I see the filled-in dot at a height of 7. Now, what I want you to notice here, very, very carefully, is that I have 3 numbers here. 2 of them happen to be the same. The functional value and then the left-hand limit, these are equal to each other. And that's the reason why it's called left continuous. Let me reiterate that with the right continuous. Let's say, again, I have a 4, this time I have a 3, and I have an 8. So what do we get? The limit as x approaches 4 from the left of f of x. Well, this is going to be equal to 8. The limit as x approaches 4 from the right of f of x is equal to 3. The functional value, f of 4 itself, no limits involved. Well, this is equal to 3. And I want you to notice that the functional value is equal to the right-hand limit here. And that's why we're going to call this thing right continuous. So these were the discontinuities in the finite sense. So let me talk about the infinite cases. So in a previous video, I had some pictures that looked like this. So I want to talk about the limits of these particular problems. This particular problem. Limit as x approaches 5 from the left of the function. What do you think it is? Well, if I'm looking at this and I approach from the left-hand side, I am going to go to positive infinity. If I take this and I look at x approaches 5 from the right, I'm going to get a negative infinity. Well, from that picture, that's kind of what we're looking at. This picture, I'm just going to say it verbally. The left limit is infinity. The right limit is whatever the y value of this filled in dot. This particular, the left and right limit are both positive infinity. This one, well, let's say this is x equals 5. The problem that I have here is if I go to 5 from the left of this function, there's no specific place that this is getting close to. This is oscillating up and down drastically. This is a does not exist. Now, if I want to add a little bit onto this and say, okay, now I have a dot and I'm going to do something like that. In this particular case, I'm on the right-hand side, the little plus sign. And now if I knew the coordinates of this dot, let's just say I have 5, 12. This answer is going to be 12. Now, even if this dot was open, it wasn't filled in, my answer would still be 12. So this is a very small introduction, rough introduction, to how to look at graphs and figure out some limits. The left-hand limit, the right-hand limit, and stuff like that. In the next video, I'll talk about two-sided limits, and that's going to be connected to all of this in a minute. Hope everybody has a great day, and if you have a question, let me know. Bye.